Imagine pointing an instrument at a planet light years away, but instead of just seeing a tiny, featureless dot of light, you could actually reconstruct a detailed image of its surface. We're talking continents, oceans, massive storm systems. It sounds like pure science fiction, right? Well, it's not. There is a real, proven physical phenomenon that could actually make this possible. Welcome to Curious Orbit. Today, we're diving into a premium space science explainer on a concept so utterly massive, the telescope wouldn't just be a machine we build from scratch, it would literally be a star. So let's get into it. So, here is the big, mind-bending question for today's explainer. Could the sun photograph an alien planet? Just think about that for a second. We're talking about using our very own local star to reconstruct surface details on worlds that are orbiting entirely different stars. Could we really see alien continents and weather systems? It's an incredibly tantalizing thought. But to figure out how we might actually pull this off, we first have to understand the massive limitations of the tools we're currently working with. You see, we've discovered thousands of planets orbiting other stars. Gas giants, rocky worlds, even some sitting right in that habitable zone where liquid water might exist. But there is a huge, unavoidable problem. They are just impossibly far away. Even when an exoplanet is considered relatively close by astronomical standards, it's still incredibly faint. A conventional telescope, no matter how advanced or how huge you make the mirror, might detect the planet's light, sure, but physically resolving that light into an actual surface map, that's a completely different beast. It's quite literally like trying to photograph a single speck of dust from thousands of miles away. We can't just build a bigger piece of glass. We need a completely different approach.
And to find that approach, we have to look back to one of the greatest minds in physics. Enter Einstein's theory of general relativity and a little thing called gravitational lensing. The basic idea here is that incredibly massive objects can actually bend the path of light by curving space-time itself. And we already see this happening all over the universe. Massive galaxy clusters act like these giant natural magnifying glasses, bending and magnifying the light of objects way, way behind them. So in a way, the universe is already filled with natural telescopes. But instead of looking at random distant galaxies, scientists have been figuring out how we might harness this exact effect right here in our own cosmic backyard.
Section 1. Einstein's ultimate telescope, the Solar Gravitational Lens.
Now this is where things shift from theoretical physics into a totally awe-inspiring mission profile. If massive objects bend light, well, what's the most massive object we have easy access to? The sun. We can totally flip our traditional understanding of astronomy upside down by using the sun's enormous mass. Its gravity curves space-time so much that light traveling near the sun follows that curved geometry. So instead of relying on gigantic glass lenses or those super delicate mirrors, we just use nature itself. The sun becomes the giant gravitational structure, and a spacecraft positioned far away simply acts as the detector, catching the paths of light coming from a distant alien world. But as you might guess, there's a pretty massive catch. You can't exactly just park the spacecraft next to Earth.
550. I really want you to let that number sink in for a moment. To make the solar gravitational lens actually work, the focal region, the place where all that lens light finally comes together, doesn't start in Earth's orbit. It doesn't start near Mars. It begins roughly 550 astronomical units away from the sun.
To really grasp the insane scale of that, let's look at our baseline. Earth sits at exactly 1 AU from the sun. Even Pluto, way out there in the freezing outer edges of our neighborhood, is only tens of AU away. Think about the solar system as a gigantic map. The outer planets are far, for sure. But to reach 550 AU, a spacecraft is entering a completely different scale of deep space exploration. The sun would still be behind it, but Earth would just be this incredibly distant, completely invisible little point.
So that raises a pretty fascinating question, right? A curiosity loop we definitely need to close. If the sun is the lens and we somehow manage to get a spacecraft all the way out to 550 AU, how exactly do we capture the picture? Do we just point a giant camera backward at the sun and wait for a flash?
Section 2. Not a normal photograph, the computational puzzle.
Okay, we need to be really clear about something. We have to distinguish this from the cameras we use in our everyday lives. The solar gravitational lens does not behave exactly like a normal glass telescope. It doesn't just create one simple, neat little focal point where everything is perfectly crisp and clear. Instead, it creates what's called a focal line. The useful lensing region extends outward like a line, meaning the light that finally arrives at the spacecraft's position has been heavily bent around the edges of the sun. It arrives in a highly compressed, incredibly distorted form.
Because of all this distortion, constructing the final image is this rigorous, multi-step puzzle. First, the sun bends the exoplanet's light.
Second, the spacecraft can't just sit still and snap a quick photo. It actually has to physically move around, scanning and collecting the distorted signal across various positions along that focal line. Finally, scientists back here on Earth have to use incredibly powerful computational algorithms to untangle and reconstruct the original planetary information. So the final image, it's the result of extreme physics, precise spacecraft measurements, and heavy, heavy computation. It is much closer to solving a vastly complicated puzzle than just pressing a shutter button.
But if this computational reconstruction works, the payoff is absolutely staggering. Instead of just asking, hey, is there a planet there? We could actually map large continents. We could identify distinct cloud patterns, we could observe seasonal changes over time, and even analyze specific atmospheric wavelengths to learn exactly what that alien air is made of. The level of detail we're talking about here would be far beyond what any ordinary direct imaging could ever provide.
Which brings us to another massive question. We know the physics works. We know what kind of amazing things we could see. But how in the universe do we actually get a spacecraft 550 times farther out than Earth's orbit and do it in a time frame that makes sense for human scientists?
Section 3. The engineering impossible. Reaching deep space.
See, the sun isn't just our lens here. It's also a massive gravitational anchor that we have to escape. One of the most thrilling concepts to solve this travel problem is called the Sundiver maneuver. And the basic idea is just as intense as the name sounds. Rather than shooting straight out into the void, a spacecraft would actually dive inward first, traveling extremely close to the sun. By combining the sun's immense gravity with some kind of advanced propulsion, like solar sail technology, right at the point of closest approach, the spacecraft would execute this dramatic slingshot maneuver that could accelerate the probe to unbelievable speeds, helping it reach that 550 AU deep space region way faster than a conventional outward path.
And you know what? We might not even just send one spacecraft. Instead of relying on a single lonely probe out in the dark, imagine launching a string of pearls, a whole sequence of spacecraft lined up along that focal line. Each one could sample different parts of the distorted signal. Working together, they would essentially act as a distributed observatory. Multiple spacecraft taking multiple measurements, all utilizing one enormous gravitational lens to piece together a much more complete picture.
But let's be totally realistic for a second. The mission hurdles here are monumental. The absolute biggest nightmare is the three-body alignment. The target star, the sun, and our spacecraft all have to line up with extraordinary pinpoint precision. And remember, that target planet is actively orbiting its star. That star is moving through the galaxy. Our spacecraft is moving. The entire solar system is moving. It is an orbital mechanics problem on an unbelievable scale. You add to that the challenges of navigating at extreme distances, trying to communicate across 550 AU, and just providing power for a mission that could easily take decades, and you start to see why this is so insanely difficult.
And that actually brings up a rather harsh reality check. Let's say we pull it off. We do all of this. We build it, we launch it, we align it perfectly. What happens if, 10 years later, we suddenly discover a much more interesting alien planet in a completely different part of the sky? Can we just, turn the telescope?
The short answer? No. Changing targets requires a completely new alignment geometry. Because you're using the sun as the lens, the spacecraft has to be positioned on the exact opposite side of the sun relative to the target star. You can't simply re-aim it like a camera lens on a tripod. Shifting to a new exoplanet would require moving the spacecraft vast distances across the outer solar system. Orbital mechanics, once again, becomes a massive limiting factor.
So the crucial point we really must stress here is this reality check. We are not building this today. It is super vital to note that this is a rigorously researched concept studied by brilliant scientists, including work associated with NASA's Jet Propulsion Laboratory. But it is not a completed operational telescope. Let me be clear, we cannot currently photograph alien cities. We just can't. This entire concept requires enormous advances in spacecraft technology, shielding, deep space propulsion, and image reconstruction before it ever becomes a reality.
Section 4. Humanity's Ultimate Telescope. So, why do scientists even bother studying something so wildly difficult? Because the potential payoff completely redefines our place in the cosmos. For thousands of years, humans looked at the stars with just their bare eyes. Then, we built physical glass telescopes. We put them on mountains, then into Earth's orbit, and then deep into space. But the Solar Gravitational Lens represents a total paradigm shift.
The next great leap in astronomy isn't necessarily about building a bigger physical mirror. It's about recognizing that the universe already contains these massive natural optical systems. It's about turning nature itself into an instrument, fundamentally redefining how we conduct deep space exploration.
It leads to this deeply awe-inspiring realization. The telescope would not be something we built. It would be something the universe already gave us. We would simply have to figure out how to step up and use it. If humanity eventually masters this, we could study distant worlds orbiting other stars, worlds with oceans, clouds, and perhaps things we haven't even begun to imagine, in a way we have literally never done before.
Well, we've reached the end of today's explainer, but the journey of discovery never really stops. I want to leave you all with a massive question to ponder. If humanity could build this telescope, what alien world would you photograph first and why? Tell us in the comments and subscribe to Curious Orbit for more space science and the technologies that could change how we see the universe.